Good morning, everyone. Chief A, are you on the call and ready to go? Babu, Chief A, are you guys there? Can anyone hear me on the call? Can you speak up?
Yes, we
I can hear you, Professor.
Okay. All right, Chief A, are you there? No Chief A. Okay. So until he joins, if you have any questions, you'll have to just unmute yourself and ask the question, okay? So let's get started. At the very end of last class, I explained to you the different forms of remote procedure call semantics that can be implemented. And the one that characterizes the ideal situation is called exactly once semantics, right? This is where the ideal semantics of local procedure call is precisely matched in the remote case. So you make one call and one execution of the called procedure happens. Not 0 times, not multiple times, precisely once. And it works even if the internet is broken, if the server dies. Underneath the covers, the RPC package has to perform heroic feats in order to make sure your procedure succeeded, right? You can build such a system. It is possible with enough sweat and enough pain to build such a system. But nobody does that. The reason nobody does that, we explored in the previous class. It is both too expensive in terms of the price you pay on normal calls, because every single one of them would have to save state to persistent storage, to disk or SSD, just in case a crash happened. And that cost slows down forward processing in the normal case. So the way to think about this is like paying a very high premium for insurance, right? You have health insurance, life insurance, auto insurance. Whether it's a good deal or not depends on how expensive it is. And basically, to meet this promise, the cost you incur, performance cost you incur, is a very high cost, not to mention the complexity of the code that you have to write. For all these reasons, exactly once semantics is a theoretical ideal. In practice, a remote procedure call package that is written by, say, offered by Google as part of their offerings like gRPC or any of the others, do not try to offer this semantics. What they all offer is something that's a little weaker, but in the normal case, when there are no failures, you cannot tell the difference, okay? So this is called at most once semantics. And at most once is the behavior in the worst case. In the average case, or the best case, the behavior is no different from exactly once. As long as there are no failures, and by failures, we don't mean one lost packet. We mean a server crash or the internet connection to the server being broken for many hours, right? So we're not talking about transient failures. In the worst case, there's about what happened. You cannot be sure whether the call was executed or not. If it did get executed, you are sure it was only once, right? So the way you can tell, if you actually get a success code back from the remote procedure call, even if there were no output parameters. You make the call and you get back success, I did it. If the remote procedure call package tells you that it did it, you're 100% certain that it actually happened, and it happened exactly once. If you get a return code or an exception that says timeout, that's when there's ambiguity. You're not sure which one of these may have happened. Maybe it got executed, maybe not. If it got executed, you're sure it was only once. But whether it happened, we don't know. And so on top of this, you layer the necessary semantics for exactly once. Now, it turns out that there are some situations in which you can choose to be even simpler. So consider, for example, checking the stock price for, say, in this example, Microsoft stock price. If you make the request and the server sends you an answer and it gets lost, and you retransmit, is it important that you get back the same old answer? I mean, it got lost anyway. And you might as well get the current price, which may be a few milliseconds later. So this is a situation in which it's certainly not a buggy outcome to re-execute the call. How many seats are left on this flight? The last call that you made, the reply was 12 seats. That reply got lost. Murphy took it away. You retransmit. Should the answer that comes back be 12? Or is it okay to give you back the answer 10? Because there's actually only now 10 seats. In fact, one could argue, perhaps, that the most timely answer in this setting is actually closer to our definition of what is correct, right? Giving you the answer we gave you the last time just to be consistent in this setting would be considered somewhat dubious, right? So if you have a system in which re-execution is not problematic, it's not like paying your gas bill. You paid once the first time. When a retransmitted request comes, you merely want to say, I already did it. Here is what I told you the last time. Here's the proof that I paid it. You don't want to repay that bill. So that was a case where the exactly once semantics or the approximation of at most once was the correct solution. Exactly once and at most once capture the intended correctness criterion. Using a mechanism such as what is on this slide, which says, we'll try it again, that's going to lead you down the wrong path there. So depending on the use case, you may or may not be able to use this weakest kind of remote procedure called semantics, okay? There's no general answer. You have to consider on a case-by-case basis and think through the correctness criteria. We refer to this as at least once semantics. It's at least once because when you finally get an answer, the only way you could get an answer is because it was at least executed once. Many previous retransmissions may have been attempted. They may, in fact, have been received. Execution may have happened. Replies may have been sent. You just don't know, right? So exactly once, at most once, and at least once are examples of remote procedure call semantics. And exactly once by far is the most stringent. At most once is weaker. And at least once is the weakest in terms of the guarantees that you get back about what exactly happened. In practice, most open source and commercial implementations offer you at most ones, because it's the sweet spot between efficiency and offering a useful building block upon which to write code. Okay? So I'm going to pause here and ask if there are any questions.
Professor, no question on the chat now.
Not yet. Okay, great. So I want to use, yes. So you're speaking too fast. Hold on. Go ahead.
Banking transactions, we would need exactly once, right?
For which one? Banking. Yes.
But if gRPC and the other commercial providers don't provide that, then what would do?
Okay, for the benefit of the class, the person who is in the room, I've got one student in the actual lecture room. He's my real live audience. So the question he has asked is, in a banking application, you actually need exactly one semantics. If the commercial package only gives you at most ones, what do? The answer is you have to manually implement exactly the mechanism that would have been implemented if the RPC package had been exactly one. So for example, you might have, let's consider the gas bill. The gas bill that is sent to you has an invoice number or a date. So you need to track. You make a payment request to the bank saying, on behalf of invoice number blah, please pay People's Gas this much money. Now the bank, that second part of it is done using at most one semantics. Suppose you get a timeout error. You don't know if it got paid or not. So what do? Well, you can send a different RPC request first that asks the bank, on behalf of me, did you recently pay invoice number blah to People's Gas? And notice this is a different RPC. The bank sends back, oh yeah, I did. Then you're done. If it says, nope, I don't see any request, I didn't make any such payment, then you retransmit the payment request. Notice now the bank does not view this as a retransmission. For as far as the bank is concerned, this is a new payment request and it'll go execute it. But you manually used the invoice number for duplicate detection. Okay? So on a case-by-case basis, you're going to have to use application-specific knowledge to effectively perform retransmission and duplicate detection. There's only one mechanism known to man on handling this kind of transient errors. That mechanism is retransmission and duplicate elimination. You just implement it in an application-specific way. Does that answer the question? You use at most once at the bottom layer in your interaction with the bank. On top of it, only in the case where you get a timeout error and you're recovering, that's when you use this application-specific retransmission mechanism. And what you're retransmitting is not a blind request, just pay it. You, in fact, are asking, did you pay it? And the assumption is that before the bank made the payment, it actually writes in a log on disk, I'm about to pay this money, right? So only for that operation, but not for many other operations. Or if it can't find it in the log, then you didn't do it. Okay, any questions, Chief A, online?
Yes. Mihal asked, can you clarify what does it mean about operation idempotency?
Operation idempotency is in the previous slide. Whoops. Idempotent means you can perform it many times. So for example, assignment in a programming language, like X gets the value 7. If I re-execute it, will the value of X change? No, it'll be 7. I can execute it 100 times and the value will be 7. So that's an example of an idempotent operation. Add 1 to X. Now that is not idempotent because if you do it twice, the result is different. So operations in which performing the operation does not change the state of the system is an example of operation idempotency. Any other questions?
Hi, Professor. Would that be don't change the state of the system after the first call?
I'm not sure I understand the question. Please ask it again.
Yeah, so if you say X equals 7, then the first time you are changing the state of the system. So
but then repeated execution doesn't change it.
Okay, so it's just that the repeated execution doesn't change.
That is the point of idempotency.
Okay.
Performing it 1,000,000 times is the same as performing it once. That is the requirement of idempotency.
Okay, thank you.
Yep. All right, let's move forward. We'll have more time for questions a little later. Yes?
Yeah, hi, Prof. I had one question related to the at most one semantics. Could you explain how at most one semantics avoids transactional storage?
Because the server is free to always reply, I don't know. So always a correct response by the server. Okay? Timeout is equivalent to I don't know. When you reboot a server, it comes back up. It doesn't have anything in volatile memory, no state. And it receives a retransmitted request from the client saying, please pay this bill. This is a remote procedure call. The server says, wait a minute, you're saying it's a retransmission. I don't have any record of you talking to me before. Sorry. Right? So, right, that the fact that that is a correct behavior is what allows you to have amnesia.
Right. Okay.
Okay. If the server upon reboot had to give an answer one way or the other, yes, I paid it, or no, I didn't pay it. And if I don't know is not a correct answer, then I must have written to disk storage before payment. That's the only way in which absence of that record guarantees that I didn't perform the request. If I didn't write to disk storage, I may have paid it. There may have been bits in volatile memory, but the crash caused them all to be evaporated. And so upon reboot, I've forgotten. I have amnesia. So the way to think about this, an easy way to think about this, is at most one's semantics makes life easy for servers to handle crashes. Because after they come back after a crash, it's like rebooting your machine. I have no recollection of any work that I was doing when I died. And if you come to me and ask me about some work, some remote procedure call you made 10 minutes ago to the previous incarnation, which died, I don't know is a correct answer.
Okay, that makes sense. Thank you.
Okay. So let us use exactly once, at most once, and all of what we have talked about to learn about something that is going to occur repeatedly in this class, okay? So this is only the first time that we're seeing it, but you're going to see it many, many, many times, okay? And that is the difference between two important properties, one called safety and the other called liveness. So a safety property, intuitively, is about something bad that cannot happen. Okay? So if I can tell you with 100% assurance that doing this action guarantees to you some bad thing won't happen, if you can guarantee me that, that's an example of a safety property. So exactly one semantics guarantees you will never pay a bill twice because of glitches in the system, because of server failure, because of network failure. The only way you can pay a bill twice is if your code had a bug in it and you actually made 2 RPC calls to pay the bill. So the bug is yours, not the system's. Okay? So that's an example of a safety property. A liveness property is very different. So think about your car. Suppose your car has working brakes. Every time you press the brake, the car stops, right? That's an example of a safety property. Now, suppose your car's engine has died, it won't start. Well, that's a perfectly good way to remain safe. If you can't move, right? I don't even need brakes. My car won't start. It doesn't even have an engine, maybe. So from a safety point of view, a car that won't start is perfectly safe. What it's missing is a liveness property. Liveness is that something good will happen. Like I can actually get in the car and move. So the difference between safety and liveness is safety properties are always about some bad event. And a safety property guarantees to you that they won't happen. So deadlocks, which you learned about if you took a class on operating system or even in 213, it's an example of a bad event. An algorithm that allows you to do mutual exclusion that guarantees to you deadlocks will never occur, that's an example of a safety property. On the other hand, starvation means I'm never deadlocked, but I never seem to make forward progress. Every time I get near the head of the queue, somebody else jumps in line. That's an example of where nothing bad has happened in the sense of a deadlock, but I don't seem to actually make progress. So that would be an example. The ability to guarantee that there's no starvation would be a liveness property. And so in the context of remote procedure call, exactly one semantics essentially is promising you a safety property. The existence of a timeout in at most one RPC is a liveness property. I have waited 5 minutes for the stupid bank to tell me success to this remote procedure call. I've still not received it. The fact that I can hit Control-C and get on with life is an example of a liveness property. In order to implement this, the code, your application logic, has to be able to handle timeouts like this correctly. It has to have internal logic that says, even if the remote procedure call timed out, I have ways in which I can find out whether the bill was paid. It's not by repeating It's not by retransmission. That's not good enough. I have an alternative mechanism. For example, another procedure call to the bank asking, did you pay invoice number blah to this person on this, date? And if the bank says yes, you have established effectively that you didn't pay twice, and therefore the liveness property is successful. Okay? Let me pause here. Any questions about safety and liveness? One footnote here. You cannot build a successful system that only pays attention to safety. Right? A car with no engine is perfectly safe, but it'll not do anything useful. So real systems have to somehow balance safety and liveness. And you will see repeatedly in this class that achieving this balance is not easy. That in fact, it requires quite a bit of work, and you can have many technically correct solutions in this space, but there are different points in the trade-off space between liveness and safety. Okay, let me pause again. Any questions about safety and liveness?
Haoshen asked, is check time function idempotent? Because each time, each message is different, but the check time function accesses the same variable and doesn't change the state.
Chife, you spoke so fast, I didn't understand the question. Please repeat slowly for me.
So Haoshen asked, suppose we have a function to check the current time. Is this function considered idempotent? Because each time the return message can be different, but the function is accessing the same variable and does not change the state.
I think the question you're asking is read X idempotent. Is that what you're saying?
Yes, and it's actually specific about reading about the current timestamp.
Well, if X doesn't change, if the underlying value doesn't change, then you're guaranteed that any number of reads will return the same value. So read by itself does not modify the value of X. On the other hand, you have variables like auto increment, right? Where the act of accessing it also increments it by 1. That's an example of an operation that is not idempotent. But anything on safety and liveness?
Yes, Lingxi asked, is deadlock free a liveness or safety property?
I didn't understand the question, Chief. Can you ask it again?
The student asked, is deadlock free considered a property of liveness or a property of safety?
So deadlock is an example of a bad event. You could equally well consider it a negative liveness property, right? To be able to say something is deadlock free is saying it's guaranteed to be live. So depending, you could consider it as liveness or you could consider it as safety. Both of those would be valuable ways of looking at it in that particular case. So a different example might be a disk that promises you, when the disk head crashes, it does so in a way that never destroys any data on the disk. So that would be an example of a safety property. Okay?
And Chihao asked, so the liveness property is achieved by having timeout in at most once RPC, but not the safety property. And he asked, is it up to the application's responsibility to handle timeout and achieve safety property?
Yes, correct. That's an excellent point. when the underlying mechanism is biased towards liveness, which is what you're doing when you say RPC has at most one semantics, then if you really need safety, you have to implement it manually on top of the mechanism. So that is exactly correct. Okay, we'll take a few more questions a little later. I want to take a brief moment to drill down a little bit into Project One. I drilled down a little bit in the previous lecture where we talked about how is it that you implement the reliable delivery aspect, the control flow aspect of remote procedure call. Do you manually do it yourself? That's not what you're doing in Project One, but you could, and I explained to you how you would do it. Your project does not have to worry about retransmissions, does not have to worry about duplicate elimination. Right? The reason it doesn't is because TCP does it for you. So this question arises more generally, when can I outsource the implementation of an important property? And when should I have to do it myself? Right? Because if you can outsource it, life is better. You have less work to do. If you have to implement it yourself, you have to debug it, you have to get it right. There's a lot of work involved. So the important observation is that TCP retransmission is actually a fair bit of work to get right. Yes, there's simplicity of code when you use it, but there's a hidden price. You don't know the price, but let me show you the price you're paying. Okay? Notice, first of all, that in Project One, if you get a timeout error on your TCP connection and you make a new connection, that new connection knows nothing about the old connection. So if you had made a request and while waiting for the reply, you got that timeout and you created a new connection to the same server, that server will not know anything about that call that was in progress on the old connection. So if you want any kind of exactly one semantics, you have to do what we just discussed a little while ago, which is you have to implement it on top of TCP. So exactly one's RPC, therefore, is not helped by the use of TCP. Okay? Now, at best, TCP is simplifying the implementation of at most one's RPC. So this is an important point. However, what is going on under the covers is that in the best case or normal case, TCP actually hurts performance. Here's why. When you send a packet to the TCP connection and you say use a write system call or a send system call and say send these bytes, TCP says, okay, I'll do it for you. Underneath the covers, I showed you in the protocol yesterday on the last lecture that TCP depends on acknowledgements from the other side. So when your request gets delivered, inside the TCP implementation, there's an ACK that comes back. So you sent the request bytes, you got back an ACK, but that ACK is not the reply you were waiting for. That ACK is like a message that says, okay, we got your request, we are working on it, we'll get back to you when we are done. You're still waiting. Eventually, the server completes the operation, sends the reply, And because it is being sent by TCP, at the TCP level, there is an ACK that is sent back to the server. So there are actually 4 network transmissions: the request bytes, the ACK for the request bytes, then the reply bytes, and the ACK for the reply byte. So there are 4 transmissions. But those 2 ACKs are unnecessary because from the viewpoint of the requester, the reply could only be sent if the request arrived. What do I need the first ACK for? And as far as the server is concerned, it doesn't really care whether you receive the reply. If you cared, you would retransmit, and the server would reply again. But otherwise, why does the server care whether you got the answer? So the important observation is that the use of TCP simplifies the average case, but it doesn't make the worst case any simpler. You still have to implement all of the processing for exactly one semantics. And it has a cost in the average case in terms of performance. This trade-off, it's a very fundamental trade-off in distributed systems. It's called end-to-end reasoning. So, also known as an end-to-end argument. So in a distributed system, when you have some correctness property, some safety property that is defined between 2 endpoints, the involvement of those 2 endpoints is essential. You need code at the level of those 2 endpoints to enforce that safety or correctness property. You cannot achieve it by offloading it or delegating it to some lower level library, because the interaction between the endpoint and the library can fail. So a server crash is such an example, and there can be many other examples. At best, low-level support can improve the performance in some cases, and that can be a very important property in the average case. Okay? So one of the optional readings, this is the first time I'm pointing out an optional reading, is the paper written almost, how many years ago is 1984? 40 years ago. Okay? Called End-to-End Arguments in System Design. I encourage you to read this because it's a beautifully written paper. Everything it said in 1984 is true today. So this is an example of ideas and logic that are technology independent. All the numbers may have to be changed by orders of magnitude. Today networks are, tens of gigabits per second, hundreds of gigabits per second. At the time this paper was written, if you got a few megabits per second on the internet, you should be very happy. Okay? But everything it says there is still true today. So encourage you to read it. But the essence of the paper is the point I just made to you. That is, in a distributed system, correctness properties or safety properties between 2 endpoints can only be achieved with the active involvement and participation of those endpoints. Lower level mechanisms can offer performance optimizations in many cases. They can also make the mainline code simpler. But the fact that the mainline code is simpler merely shifts the complexity to the error handling code. There's somewhere in your code, there is the complexity to deal with failures. Okay, and this is a quote from the paper. This paragraph here is the statement of the end-to-end argument. And the way to think about what it's helping you do is if you ask the question in a distributed system, where should I put some code? How should I layer my system? Who should have responsibility? Right? These are questions that you'll face repeatedly. The answer is, between what two endpoints do you want your safety property? That will have to be the layer which implements ultimately the guarantee that you're talking about. So let's take an example. Suppose I have here in class, there are two people sitting here, three people sitting in the room. Let's say they all have laptops, okay? And one of those people is running a Firefox browser on an Ubuntu system, which is what I'm showing you. That person is connected via CMU Secure, the wireless network. In this room on the wall, over there, and many other places on the wall, are the access points. So the packets transmitted, assuming it's sent by TCP, or it could be sent by UDP, the first place it goes to is the Wi-Fi access point. From there, it goes over the CMU wired Ethernet to a specific node, which is the point of connection of Carnegie Mellon to the internet. And that's the point at which your packets, come back. Yes. That's the point at which your packet is introduced into the internet. Now, the internet itself is very complex. So let's say you're performing a remote procedure call to, let's say, check a bank balance or make a payment or make an airline reservation or purchase something from Amazon, right? Some standard operation. That packet is going to go through many hops on the internet. You don't know how many. And this is constantly changing, right? So it goes through all these hops. Finally, when it gets to your bank, like Bank of America, or it gets to the airline, say Delta Airlines, or somebody, it gets onto their local area network. It then arrives at the server, which has a web front end, and then an application server. So this could be something like an Apache server. The application server could be something like Tomcat, if you're using an open source model, or it could be something like WebSphere, and so on. And then finally, there's a database, like an Oracle database or a DB2 database or a SQL Server database from Microsoft, which contains the persistent state. If you're Amazon, knowledge about how many widgets I have of, say, some particular article is in that database. When you sell one of these things, you have to change the value in the database. That's how I'm able to tell you when you ask, if I buy another one, when will I get it? It's able to say, I'm sorry, I'm down to 0, it's on back order. Or I'm able to say, if you want 3, I can give it to you right now, right? Same thing for airline reservation, same thing for your bank balance, right? So this model of a web server, an application server, and a database is a very common approach in web-based e-commerce and other systems. So when the user here says, please perform this operation, which are the endpoints? If I'm only looking at TCP acknowledgements, the TCP connection is between my Firefox web browser, which is this endpoint, and the Apache server. So when the TCP level acknowledgement comes back saying, yes, your packets were delivered, that guarantee only means the packets were delivered to the Apache server. But in order for your purchase, like an airline seat, to actually be effective, it has to be registered in the database. Many things can go wrong between here and here. So if this application server dies, the fact that the web server said, I got your package means nothing. If your ticket was actually purchased and the change was being made to the database, but just as this database was trying to make the change, the server crashes. Right? Because the server crashed, your seat was not really reserved. When you get on that plane and try to board, you'll find, hey, somebody else is in my seat. Well, presumably you wouldn't get to that point because you wouldn't have got a boarding pass to get there. But you get my point. That is, the fact that you got an acknowledgement that your operation was performed only says your packet got this far. It doesn't wait. If you wanted that promise, the Apache server would have to wait until it gets an acknowledgement back from the database. So only then can it say to you, not only did I receive your request, I've also performed the operation, the bits have made it to the disk, and I have been assured that those bits are on disk. And so when I send you this acknowledgement, you have that guarantee. In that case, the endpoint is now the database rather than the web server. So clearly identifying the endpoints involved in an acknowledgement and exactly what they're acknowledging is critical to end-to-end reasoning in this system. And exactly one semantics is only as good as the endpoints between which the information was provided, right? So for example, if you go to the post office and you say, you know, regular mail is kind of flaky, I want to use certified mail. Well, if you get back an acknowledgement that says your envelope with label number blah was successfully delivered to the IRS on this date, you feel very happy because it got delivered. Well, but you know what? The delivery was only to the mailroom. Between the mailroom and the person who should actually process it, many things can go wrong. You'll never know. All the post office can promise you is we delivered it to the mailroom. From there, did it get lost inside the IRS? There's nothing that the post office can do to help you. So end-to-end reasoning is crucial, and this picture repeatedly is a valuable one to think about as you think about this property. Let me pause here and take questions. No questions, Chife?
Xinyang Wang asked a question about the previous contents. He asked, can you explain again, why does TCP simplify at most once?
Why the TCP, repeat what you said, why the TCP?
Simplify at most once
Why
RPC.
at most once?
Yeah.
Oh, look at project 1. Are you writing any code for retransmission? Are you writing any code for duplicate elimination?
No.
The fact that you don't have to write that code is proof that, in fact, use of TCP simplifies the use of at most one semantics. If there's a bug in your code, and when you make the RPC, if the server dies, the TCP connection will break. When you bring up a new server and establish a new connection to it, it won't remember anything about the old connection. So what you have right now in project 1 is TCP is helping you achieve at most one semantics, but you don't have to have the pain of doing retransmissions, duplicate elimination, etc. It's doing it for you. So that's the simplification. Does that answer the question?
Professor, but can you explain the difference between exactly ones and at most ones? But why doesn't it simplify exactly ones?
Oh, because if the server dies and the previous, so suppose you perform the request. Your request is successfully delivered to the server. The outbound TCP connection tells you, yes, I delivered it. Well, the fact that it was delivered is only proof that it got as far as the server. It could be queued up waiting at the server to be handled. They have a queuing mechanism. Or let's say the server started work, but because of a bug in your code on the server dies. It gets an illegal memory reference and just dies. What do you see on the client? You see TCP connection timed out, right? The act of having to establish a new connection and then asking the server, did you actually pay that bill? You still have to do it. TCP can't do it for you. Maybe the server died after it paid the bill, but the bug was in code dealing with sending you a reply. So the work was done, the bill was paid. It's just that I made a stupid error in the code to send you the reply. And so from your perspective, you don't know. You still have to find out. Okay, does that help?
Yeah, thank you.
Okay, any other questions?
Yeah, so in this example you give, are you saying so it should be the laptop and the database be the two endpoints, or?
So the question is, when does TCP send an acknowledgement? All right, the implementation of TCP says, as soon as the bits arrive here, that's the socket on the server side. When they've actually landed there, it can send an acknowledgement. It's done. The job of TCP is over. But from your application's point of view, the job is not done yet. Your airline ticket is not purchased successfully until the database has been updated. So a bug in the application server, or a bug in the database, or a crash of the machine after your bits got delivered, there's no guarantee that that acknowledgement at the TCP level achieves anything in those situations.
Yeah, so you're saying we should have a TCP endpoint as well as application endpoints? Is that what you're suggesting?
Yeah, so if you want, so this is the whole point. An acknowledgement from TCP can only be a guarantee that bits were delivered between the endpoints of TCP. If you wanted assurance that the bits got written to the database, there needs to be an explicit application level mechanism that waits for confirmation of the write and only then sends back an acknowledgement. That cannot be a TCP level acknowledgement. It would have to be an application level acknowledgement. So let's say we have IBM WebSphere here. Let's say the code that you have written here directly does a write to the disk. If you did that, you wait until the write completes. You look at the return code of the write. And if the write was successful, assuming that the right return code, success return code promises to block until the bits are on disk. So when you get a success, you're sure those bits are on disk. At each layer, you have to ask, what is the promise? When will write give you a return code back? If write gave you a return code back, even without waiting for the disk write, then it's not very useful. Right? In fact, in practice, you have to use the fsync system call to make sure the bits are actually on the disk. Does that help you?
Yeah, I hope so. Thank you.
Okay, any other questions?
So Serena asked, so does it mean that exactly once is typically good for the case when the database is an endpoint?
Yes, in most cases, the persistence property and the ultimate truth resides in the database. And therefore, proof of completion of an operation is needed from that level. So the database needs to say, yes, your SQL command to update this value was successful. Then that success code can be passed up to the application level. The application says, great, the database server has acknowledged to me. And then that success code can be passed back via Apache, for example. And eventually that'll make its way to a packet that is transmitted by TCP. But the body of the message in the TCP is, I verified that on January 27th, 2022, at 11:07 a.m., the bits corresponding to your airline seat were successfully written to the airline database. That is the promise in that case. That is the only promise that you actually have that airline seat, right? The TCP ACK that says, yes, we received your request, just merely said we received your request. Anything else, Chief A?
Nadim asked, does TCP send an acknowledgement per packet, one for each packet?
Remember the picture that I drew in the last class? TCP sends acknowledgements for a byte number. So it says in this continuous stream of bytes from the other side, I have received everything up to and including byte number 973. A little while later, it'll say, I have received everything up to and including byte number 2754, and so on, monotonically increasing. So because sequence numbers are always increasing, the ACKs guarantee to you more and more of the pipeline have reached the other side. Question that I think you're asking is, when does TCP send the acknowledgement? Does it send it for every byte? That would be very expensive. Does it send it for every 1 million bytes? You could make it work that way. The problem now is you have to wait a long time before you discover whether your bytes were successfully transmitted. So in practice, the details of precisely when and how frequently acknowledgements are transmitted is typically a low-level decision that can be made adaptively, that can be done a number of ways, but that exactly how frequently you acknowledge in a byte stream is kind of a performance-related detail in the system.
Professor, I have another question.
Yes, go ahead.
Yeah, so the reason why we don't need to write any code for retransmission is because is it because TCP guarantees the server gets it?
Yes, correct.
Okay, thank you.
That's it. You're relying on the TCP guarantee. Okay, so to help you think through exactly this line of reasoning that we talked about, let's imagine I have a 3-hour long video, a big movie. I don't know what movie is 3 hours long, some movie. Okay, let's say the total MP4, the video size, let's say it's 10 gigabytes. Long movie, it's a huge file. And I want to transmit it to my friend who's far away on the internet. So I could do it in one of two ways. I could send the full 10 gigabytes, and then I could wait. And my friend eventually can tell me, give me an ACK when all 10 gigabytes have arrived. And I'm done. So the best case works very nicely. I don't need any acknowledgements before the end of the transmission. If I don't hear back after some amount of time, what do? I send him the hell 10 gigabytes again. Maybe this time they'll all arrive. My friend on the other side promises never to send the reply saying, yes, I got it, unless he gets every byte. So if even one byte was lost in those 10 gigabytes, he says, I'm not going to send any acknowledgement. I don't have this one byte in the middle of the file. So you could spend all day retransmitting these 10 gigabytes. If there's even one occasion on which it makes it through completely, that person will send an acknowledgement saying, I got it. Of course, Murphy, remember Murphy, your dear friend, who's been watching and waiting? When your friend sends that packet that's saying, I got all 10 gigabytes of yours, that's the packet that he destroys. So your friend actually got the 10 gigabytes. He even sent the reply, but you still don't know whether he got it. So what do? You send the 10 gigabytes again. And this goes on and on. All you can know is if you ever once successfully got back success code from your friend, you're done. Until then, you're going to flood the internet with repeated retransmissions of your 10 gigabytes. Notice correctness is not violated here. The correctness criteria is you declare victory only when you're sure your friend has gotten the movie. And this correctly behaves. It's wasteful. It probably heats up the planet. It probably does all kinds of bad things. But from the correctness criteria that we stated, it's correct. A different approach says, let's not be so stupid, okay? It says, let's say chop the file up into much smaller pieces, maybe 1 megabyte pieces. I send the first megabyte. I say, this is megabyte number 1 of 10 gigabytes. And your friend sends back the acknowledgement, I got megabyte 1 of 10 gigabytes. Then I send megabyte 2 of 10 gigabytes, and I get the ACK for that. And I go on. This is like a remote procedure call. Now, if I have to retransmit, I only hit retransmit 1 megabyte. Because once I get confirmation that the megabyte got across, I never ever have to do that again. I move on to the next megabyte. So by chopping up the file into smaller pieces and getting more frequent acknowledgements, the wasted work in case of packet loss, in case of network failure, is reduced. But notice it doesn't help the correctness guarantee. I still need to wait until all megabytes of the 10 gigabytes have actually arrived. And I still need to wait for the very last confirmation that is sent by the server to actually arrive. And Murphy can still throw that away. The difference is when he throws it away, my retransmission will only be of the last piece for which I'm waiting for confirmation. It won't be the full 10 gigabytes. So the two methods are equivalent from a correctness point of view. The chopping up into small parts and transmitting, the difference is visible only in the case of a flaky network. Okay? You are involving many more transmissions and many more acknowledgements. And the value of doing it is that the amount of repeated work is reduced in the case of a flaky network. So in general, a good rule of thumb is the flakier the system, the smaller the chunks of work, and the more carefully you need to babysit the process of transmission or execution. As you have confidence in the layers of the system, you can reduce the frequency of checking, but correctness still requires, and the end-to-end argument still requires that you need to do the end-to-end check that the whole thing was received. Okay? So this is a perfect example of the end-to-end argument in practice. Any questions? Okay.
Nothing in the chat.
Okay, good. So it's all very clear. Now we are done with remote procedure call. But I'm going to use remote procedure call in our discussion today to help you see a very important property of distributed systems, which is the biggest complaint you will get about them is that they are slow. Right? You had this piece of code that worked perfectly fine. It was very efficient. The interactive response was crisp. We now move to a server-based system. We put the bits remotely. I have a great network, and everything runs slowly. What's going on? Why is this happening? This happens repeatedly. And understanding the origin of slowness, slow response, is actually important. Now, a key point to note is that end-to-end latency, which is another way of saying response time, is not just psychological. People have measured the impact on business. So here's a quote from Marissa Mayer, who was the CEO of, I guess, Yahoo, but at the time she made this quote, she was at Google, right? That a half a second delay, 500 milliseconds, caused a 20% drop in traffic. That's a long time ago. I mean, it's 2008, so 13 years ago, but the property is still true today. Here's a person from the Google search team. A full 400 millisecond delay, so roughly half a second, same as what Marissa Mayer said, changed by roughly 0.5%, 0.6%, the number of searches per user. Now you think, come on, that's such a minuscule amount, 0.5%, 0.6%, how can it matter? Well, when you have 100 million users, okay, 0.6% less from each of them is a direct hit to your bottom line for that quarter. Okay? In Amazon, so this guy, it's a very interesting number. Every 100 millisecond increase in load times decreased sales by 1%. 1% is a huge amount. Can you think of how much business Amazon does per year? 100 millisecond increase in the time it loads to a page. Effectively, this is what they discovered, that people give up. They say, oh, I'll try later. System is slow. It affects the bottom line, okay? And so this is from Bing, a search engine that I don't think is very active these days, but essentially the same point, that on the positive direction, when they were able to use edge computing, edge caching, to improve response time, it in fact increased the amount of use people made of the system. So if you have a revenue model, which is based on the number of clicks, this is direct business relevance, not by small amounts, but by huge, huge amounts. So let's go back to this picture that I showed you. All right, this is a hypothetical user in the classroom here with a laptop, using Wi-Fi, getting to the campus wireless wired network, going over the internet to some e-commerce site, which has got a web server, an application server, and then a database. Right? This is the situation. What the user is seeing is that the system is sluggish. I click on the link in Amazon, and before the page gets updated with new information, it's taking forever. The question, you, who is just hired to Amazon, fresh out of CMU, your task is to improve performance for this guy. So where do you start? You can say, oh, it must be the case that the CMU wireless network is heavily loaded. Right? This link is slow, so don't blame it on us. Or maybe the CMU wireless network is doing just fine, but the internet is horribly congested. Or the internet is just fine, and the wireless network at CMU is fine, but some bad people are doing a denial of service attack on the Amazon server, effectively slowing it down, giving it junk work to do. And so your request gets to here real fast, but then the processing, the handling inside here, going to the database to look up, coming back, constructing the web page for you with the result, and then sending that web page back, that is now slow. The point is, you don't know. Notice that all you have is information at the endpoint. So the key observation is that every step in the story, in other words, including between hops on the internet, adds three kinds of delays. The first is it adds processing delay. Even inside the internet, if I look at hop 3, this is some router somewhere in the internet. Maybe it's in the Rocky Mountains, it's in Denver. Okay? It doesn't do much. Packets come in, it looks at the address, and then puts it on one of the many outbound queues that it has saying, this is going to go in this direction. So the processing is minimal. But you know what? Minimal might still be a few thousand instructions. And a few thousand instructions could be some number of microseconds. Okay? So processing delay is one source of delay at every hop. Second is queuing delay. It's easiest to understand on the Wi-Fi access point. If there are 5 people in the classroom, all of whom are doing this, all of their packets need to be transmitted to the Wi-Fi access point and then delivered over the LAN to the internet and so on. So there's queuing delay because these interfaces can only handle one packet at a time. Your bad luck, you arrive last, you typically will have to wait. And then the last piece, transmission on a network is very fast. It's very close to the speed of light. Okay? But it's really not at the speed of light. It's often 10 or 100 times slower, might be even much slower. Certainly wireless networks are much slower. But the delay, propagation delay, transmission delay is a third component. Notice that these are three different sources of delay. And every element in here involves all three. Even if the operating system did nothing to read your 100-byte packet from the Ethernet, put it into a memory buffer, and then copy it from the memory buffer all the way up through the internals of the operating system, and then copy it into your address space, that takes some number of cycles of processing time, right? So given that these are the three sources of delay, and you have so many hops, this is why understanding the reason for slow response is very difficult. And the sad news is that of these three, processing delay and transmission delay are the easiest to address because you can usually speed up the processor, you can get a better network, but they are rarely the culprit. The culprit is very often queuing delay, and queuing delay is very, very difficult to reduce. The reason is because of some fundamental facts about queuing theory. Okay? So many of you, I'm sure, have seen the series of books, right? XYZ for C++ for Dummies. Name it. Office 2013 for Dummies, and so on, right? So I'm going to give you a grossly simplified level at this level, queuing theory for dummies. This book doesn't exist, but this one slide I'm going to give you is queuing theory for dummies, okay? So here's the iron law. All of queuing theory simplified into one slide. Now, I have colleagues, Moore Harkel-Balter, Weina Wang, whose entire research careers are in queuing theory. So, you know, there's a lot of good stuff, a lot of very sophisticated analytical methods. This is a gross oversimplification, but simple doesn't mean wrong, right? So the intuition I'm giving you on this slide is really at the heart of what queuing theory is all about. Basically, there are three attributes in a system or any component of a system. One is utilization. How heavily is it used? How much of the time is it busy? Okay? So think about a highway, a 4-lane highway. If almost all the lanes are empty, a lot of the time, then the utilization is quite low. And if you have a highway like that, somebody somewhere is going to ask, why did you build this highway? Why do you build it to have 4 lanes? Given that nobody seems to be driving on it, morning, day, and night, it's almost always empty, you over-provisioned the highway. And by doing that, you paid a lot of money to build this 4-lane highway. If you work at Google or Amazon or Microsoft, and you have this kind of a situation, your manager is going to ask you, why did you buy such a big server? Why do you put such a fast network? Why do we spend so much money on it? You could have easily used a much cheaper, lower performing component whose utilization would be higher. So from the viewpoint of cost and economics, high values of utilization are viewed as a good thing. Okay? If you're getting your MBA from Tepper, the way you get a pay raise is by finding some underutilized component in the system and showing how a cheaper version of it will do. And that's your bonus for the next year. Okay? So that's unfortunately only one attribute. The second attribute has many names. This is what you experience as a user. It's referred to as latency or response time or agility, right? Any of these names. How long do you have to stare at the screen before the page is refreshed with the result you're looking for? This is what you care about. Those comments about 400 milliseconds and reducing sales by 1%, et cetera, this is the property that they're referring to. Okay? Unfortunately, there's also a third complicated property. A very simple concept, though. I'll call it freedom. When you decide to use the highway, you don't have to ask permission. You just drive and you get on the highway, you're done. That's freedom. If I had to make a booking that says, I want to get on the highway at 2:03 p.m., that's a much more regimented way of handling things. But what it allows the system to do is to say, you know what? Too many people are asking to get on the highway at 2 p.m. Say no to some of them. And so they don't even attempt to get onto the highway at 2 p.m. They're asked to come at 3 or 4. So you're able to control the arrival pattern that is trying to make use of the resource. So networks today, almost all networks, certainly the networks like Wi-Fi and Ethernet and others, they have complete freedom. Your program, when you do that write system call into your TCP socket, you just write. You don't ask permission to do the write. Okay? So here's the bad news. I'll give it to you and then we'll stop and we'll discuss it more in the next class. So the bad news is you can have any two out of these three, but you cannot have all three. That is the fundamental message of queuing theory. Okay? If you have to remember one slide, this is a slide I want you to remember. You can have utilization with low latency, but then you have to give up freedom. You have to have a regimented scheduling policy that is not free for all. Or you can have total freedom and you can have high utilization, but you will pay the price in that there will be long delays. You see this on the highway. The long backups. How did it happen? Well, everyone wanted to leave. They all got on the highway. We're all free to do so. The highway is packed, 8 lanes, full of cars, bumper to bumper. So the utilization is high. That metaphor applies to the internet. It applies to the wireless network. Every one of these, this property is true. And so the reason for slow response, okay, is very often because economic decisions dictate high utilization and application design doesn't allow for a controlled arrival pattern. And therefore, since 1 and 3 have been optimized for, the price you pay is steep. Okay? So we'll look at this in greater detail in the next class. Thank you.